All right, so the College Board has just released the Calc BC questions for the AP exam for the year 2023. And I wanted to go through the questions and just show my approach and how I'd go about answering these. They have not yet released their scoring guides, but as soon as they do, I will post them in the description below. And you can also find a link to their questions in the description below so that you can follow along and work these through with me. So let's look at the first one here. This is the first question from the free response portion of the test involving a calculator. This is also happens to be the first question on the AB exam. So if you took the AB version, then you should recognize this question as well. So it says, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function. I'm going to underline that word, differentiable function. Usually if they're pointing that out, that means something. F, where F of t is measured in gallons per second, I always like to underline the units so I know what I'm going to be responding with. And t is measured in seconds since pumping began. Selected values of F of t are given in the table. So it's important to also note that this function that we are given, F of t, is giving us a rate of flow. It's not giving us the amount of gasoline, but actually the rate of flow of gas, and that will come in handy later on. So we'll take a moment, look at the table, and in part A, it's asking us in correct units, interpret the meaning of the definite integral from 60 to the 135 f of t in the context of the problem. So again, since we know that f of t is the rate of flow of gas, and if we are integrating a rate function, what we then have is the total amount accumulated in that interval. So we can then say that this integral, so I'm going to actually just rewrite it here, from 60 to 135, we can say that this function, this rate function, integrated from 60 to 135, is going to give us the amount of gasoline, I can just say gas, in gallons that were pumped between 60 and 135 seconds. Okay, so that's the first part of that question. Then it asks us to actually approximate that value using a right-Riemann sum, and it's giving us these three subintervals from 60 to 90, 90 to 120, and 120 to 135. And this was the part that I initially glossed over because I was a little bit in a hurry. But you should notice here that this interval has a width of 15. So each subinterval does not have the same width. So we're going to go ahead and find that approximation. So we're going to say that f of t from 60 to 135 can be approximated using the following Riemann sum. So I'm going to take the width of each subinterval times the height of the first two. So from 60 to 90, since it's a right Riemann sum, we want to evaluate the function at 90, right? So we're going to actually evaluate the function. This here is going to be f of 90. So that's going to give us the height of the first rectangle. So that's going to be 0.15. And then the second rectangle, or the second subinterval, is also going to have a width of 30, but that height is then evaluated at 120, which is going to be f of 120, which is what we want to use. So that's going to be 0.1. And now if all the subintervals had the same width, we could then just move on and continue to add the next one. But since the third subinterval actually only has a width of 15, we're going to say 15. We then want to find the height at 135 of that rectangle. At 135, which is going to give us this here, f of 135, which is going to be 0.05. If you punch that into your calculator, you get 8.25. And again, what does that number represent? That is the amount of gas. That is the amount of gas in gallons that were pumped from 60 to 135 seconds. All right, so the next part. So let's look at part B. Must there exist a value of C for C being between 60 and 120, non-inclusive, such that f prime of C is equal to 0? Justify your answer. So if you see the structure of this question, this is a clear setup that we want to use the mean value theorem here. Okay, so we can then say the following. Well, first off, what is the justification or the conditions for us using the mean value theorem? The function has to be continuous and differentiable. And since it said in the problem that the function was indeed differentiable, remember I highlighted that earlier, since it is differentiable, I can then say, since f is differentiable, and by definition continuous, by the mean value theorem, also known as MVT, but if you're writing this on a test, you should write out the full theorem name. There must be a C value. There must be a C value. And remember what the mean value theorem says, right? The mean value theorem says that if your function is continuous and differentiable, then on this interval, there's got to be some value of C that provides the rate of change that gives you the same value as the rate of change. So we're going to say here that f of 120 minus f of 60, again, what we're calculating right now is the average rate of change, 120 minus 60. And this is going to come out to 0.1 using our table, minus f of 60, which is also 0.1 over 60. And this is equal to 0. So the mean value theorem says, assuming that these conditions of the function being continuous and differentiable are met, there's got to be some value of C where the instantaneous rate of change, f prime of C, the instantaneous rate of change, is actually equal to the average rate of change. It's got to hit that value at some point. So since those conditions are met, we know we're good here. All right, let's move on to part C then. Part C, it says, the rate of flow of gasoline in gallons per second can be modeled by this function G. I'm not going to read all that out. You can see it there, from 0 to 150. So using this model, find the average rate of flow, and I'm going to underline that, the average rate of flow of gasoline over the time interval from 0 to 150. And we're going to show our setup here. Well, this is just simply the average value of a function. So I'm going to say that the average value of this function G is, and we're going to use this formula, it's the definite integral from 0 to 150 of this function g of t dt divided by the width of that function. So since we are looking, or the width of that interval, I should say, or the length of that interval. So since we're going from 0 to 150, I'm going to divide that definite integral by 150, or multiply by 1 over 150. Punch that into your calculator, and you should get either 0.096 or 0.095 if you are truncating. Okay, pretty straightforward there. And let's look at the last part of this problem. Using the model G defined in part C, so using the previous function, find the value of G prime at 140. Interpret the meaning of your answer in the context of the problem. So let's go ahead and find this derivative evaluated at 140 first. So we can just do all of that in your calculator. So if you enter in g of t, which again was this function up here, put that into your calculator and find the derivative of this function at 140. So that is to say g prime of 140, you should get negative 0.05 or negative 0.005, sorry about that, 0.005 or negative 0.004. Again, depending on whether or not you decide to round or truncate. So that's likely one point. And the second part is probably going to be given to you being able to interpret the meaning of this answer. So since we know that g of t is a rate, since g of t is a rate, and we're finding the derivative, we're finding the rate at which this rate of gas flow is changing. So I'm going to write it as the following. I'm going to say the rate of gas flow is decreasing, because our value was negative, is decreasing at a rate of 0.005 gallons per second per second. And I pretty sure that you also probably should have been able to say, or seconds squared, or second squared, at the time of 140 seconds. Okay, so again, since g of t is giving us a rate of gas flow, and we're looking at the derivative, we're looking at the rate at which that rate is changing. And since it was negative, we say it's decreasing at that following rate. All right, so that was the first question of the 2023 Calc BC FRQ calculator portion.